Thank you for the introduction. It's a long title, so it's my great pleasure here to attend this conference in honor of the 60th birthday of Professor Matthias Hilbert. I met him in 2014 in Imba at Brazil. And that time, we have some discussion about both the liquid crystals and the primitive equations. And that time, I think maybe that time, at that time I'm working on primitive equations, and I think Professor Matthias Hilbert is very interesting about this topic at that time. So we have some discuss about this topic. As I will talk about a couple system of the primitive equations with nonlinear moisture dynamics. And this is the model for the large-scale atmosphere dynamics. And the moisture here, the moisture system that we consider will have several components of the moisture. And between different phases of the moisture, that will have the phase changes. And we will show the global well-posedness for this system. And this is joint work with Sabine, Hittmeir, Klein, and Titi. So here is the outline of my talk. I will first introduce the system that we will consider in both the polar coordinate and then to the pressure coordinate. And the final system that we will consider is actually in the pressure coordinate. And then we will state the mathematical setting of our problem and state the main result. And next, I will outline the proof of existence and uniqueness separately, and finally give the conclusion and some future works. So here is the system. We assume x, y, z is the polar coordinate, and the capital V is the 3D velocity. V is the horizontal component, and W is the vertical one. And rho is the density, T is the temperature, pressure is P. And we assume the ideal gas, so P is given by R set. R is the individual gas constant. And d by dt F is the total time derivative of F governed by this given velocity V. So the conservation equations for the atmosphere are the following three. The first one is the conservation of mass. The second one is conservation of the momentum. And the third one is the thermodynamic equation. And here, G is the gravity constant. Cp is the heat capacity. dVV, dTT are the dissipative terms. So we will consider large-scale atmosphere. So the aspect ratio of the vertical height compared with the horizontal width is very small. And under this condition, by the scale analysis, we will then have the hydrostatic balance is this one. And note that this density rho is positive, and G is the positive constant. So this tells you that the pressure is monotonely decreasing with respect to Z. So because of this one, we can change the coordinate. We changed coordinate from the aura to the pressure. So then we define the vertical component of the wind, which is the total time derivative of the pressure P. Recall that P is decreasing in Z. So for positive ohmic means downward winds, and for negative ohmic means the upward wind. And then we use the hydrostatic balance. we found that the density equation is due to an incompressibility condition on the new velocity v tilde. And here we take ohmic as the step component of the new velocity. And by direct calculations, we also find that the total time derivative for the function f in polar coordinate governed by velocity capital V is exactly the total time derivative of f in pressure coordinate governed by this new velocity. So we can just forget this conservation of mass equation and replace this one by this incompressibility condition in the pressure coordinate. And then we have the following reduced system in the pressure coordinate. And you can see that in here we only have the horizontal momentum equation because V is the horizontal. And its vertical momentum equation is replaced by this hydrostatic approximation in the pressure coordinate, and this one is the replacement of the conservation of mass, and of course this one keep the same. And here the phi is the geopotential, is exactly gz of the z coordinate, because now we use p as the new coordinate, then z is an unknown. And we have the dissipating terms, and we have st is the source term, which will be contributed from the moisture. Okay. And dv and dt we put in this way. However, I should mention one word that this one is not exactly the reduced system of the original one from the Euler to pressure, because the real dissipating term, the real reduced dissipating term is not in this way. Actually, some actual terms involves the one derivative of phi and two derivative of phi. We ignore that. So this is somehow a simplified system. However, this is the widely used primitive equation in the atmospheric dynamics. So we now coupled the system with the moisture. And today we will consider the warm cloud. For warm cloud, we have three phases of the moisture. We have the water vapor, the cloud water, and the rainwater. So we also have the phase changes. We have the evaporation, condensation on the collection by falling rain, and the autoconversion. And of course, these phase changes are not unconditional. We need some conditions. That is, the evaporation only happens when QV is less than this QVS. QVS is the threshold of the evaporation. That is the saturation mixing ratio. And it's only when QV bigger than QVS, that is oversaturated, then the condensation happens. And this correction by falling rain always happens. But for this autoconversion from the cloud water to rainwater, we need enough cloud water. Okay? So from this picture, we will then have the following moisture system. We just take QV as an example to explain its meaning. So this is the QV, right? So this tells you that the evaporation will contribute to the increasing of this QV, and the condensation will contribute to the decreasing of this QV. This is this matches our physical understanding. Okay, and here we have constant Vt here. This is the terminal velocity of the falling rain, because when there are enough rain, the raindrop is big enough. Finally, it will drop down to the ground. So then we couple these two systems together, and we have a fully coupled system. So now let's recall some known results about the coupled system. And here, the list here is far from complete. For the primitive equations without coupled to the moisture, there are a lot of works. The global existence of weak solution but without uniqueness goes back to 1990s by Liang and Wang. And the global existence and uniqueness of strong solutions, even in the 3D domain, for the full viscosity case, was proved by Cao and Titi, and also by Kopkov, Kukovica, and Sian. And recently, Hittmeir and his collaborators further developed by relaxing the assumption on the regularity of the initial date by using the maximal regularity theorem. And it happens that even with the global well-posedness of strong solutions also hold with only horizontal viscosity, that is without the vertical viscosity. And this is proved by in my recent joint work with Cao and Titi. And as a sharp contrast to the viscosity case, whether with full or horizontal. For the inviscid case, that is, we don't have any viscosity, then the system may blow up in finite time. This was proved by Cao and Titi and Wang independently. And the coupled system of PES with one component moisture was considered before by Guo and Huang, and Corti, Zlati, Huang and Kukovica, Hittmeir, and M. However, they focus on the one component moisture. And for moisture system that with multi-phases and with phase changes was proved by my recent joint work with Hittmeir, Klein, and Titi. So in today's talk, we will consider the full coupled system of the primitive equation and the multi-phase moisture system. Okay. So here's the final system that we will consider. And you can see we have the hydrostatic approximation and the incompatibility condition, and we also have this term. This term let's come from initially the fluid is compressible, and we will see that this red term will bring us some trouble improving the boundness of T. And then we need to give the explicit expression of these source terms. And here are the source terms of this evaporation, collection of the rain, and the autoconversion and the condensation, and the source term of the T. And here I just emphasize that the SEV here is maybe only holder in QR, because this index bit is allowed to strictly less than 1. And in that case, it will be cause some difficulty for us to prove the uniqueness. And all these capital C are constants, and this L is also a constant. It is the latent heat. And Cp is the heat capacity. Here is the domain we will consider. It's a cylinder domain. And the pressure is between P0 to P1, and both are positive. And then we have 3 portions of the boundary: the top, the bottom, and the side. And here are the boundary conditions. On top, we assume there is no vertical wind. And we assume that Vt and moisture Qg satisfies the homogeneous Neumann boundary condition. And at the bottom, there is some friction of the wind due to the friction between the atmosphere and the ground. And we assume again that there is no vertical wind. And we assume the non-homogeneous Neumann boundary condition on T and Qg. And the same similar to the side boundary, but on side boundary we assume it is a strip boundary. And all these blue quantities are assumed to be non-negative constants, and all these red terms are shown to be non-negative functions with suitable smoothness, and we need the initial condition. For the saturation mixing ratio, we assume the following three physical assumptions. QVS is non-negative and uniform bounded, and QVS does not vanish only on some reasonable temperature interval, and QVS is uniform Lipschitz in T. The first two will be used to guarantee the non-negativity of the temperature and the moisture, and the third one is used to guarantee the uniqueness. So under this assumption of the QVS, and we assume that initial date is H1, and the temperature and the moisture is non-negative and uniform bounded, and with this natural comparability condition on V0. And then we show that there is a global in-time solution to the corresponding initial bound value problem of the coupled primitive equations with the moisture system. And T and moisture preserve the non-negativity and the uniform boundedness. And Vt, Qv, Qc, Qr satisfies the standard regularity of the parabolic equations. So now let's go to the existence. The local existence is based on the following approximated system. And here the red terms are modified from the original source terms. We put the positive sign on the shoulder of these quantities. It will be given in the next slides. And here, recall that this SEV may be only Holder regularity in QR. So in order to we regularize this SEV by a parameter epsilon. And now all these source terms are Lipschitz in all the unknowns. So therefore, the local well-posedness of this approximated system can be proved in the standard way, say by the iterative argument or by the constructive mapping principle. So here is the modified source terms. Let's say we put the positive sign on T, Qc, Qr, and Qv. Of course, physically, because all these terms should be non-negative, but as PDEs, we need to guarantee it from PT itself. So we first put the positive sign here, right? And we smooth the QR bait in this way. We break the bait into 1 plus bait minus 1. And for this one term, we don't make the change, just put the positive sign. But for the beta minus 1 term, we plus epsilon to regularize this QR. And of course, this term is now Lipschitz in QR. The reason that we do in this way is the following two. First is that this SEV epsilon is controlled by SEV. And SEV epsilon product with QR negative part is always 0. And this is important to show the non-negative of this QR. And you can see that if you say we try in this way, then the second one is not satisfied. And then we cannot guarantee the non-negativity of QR. So we do in this way. So in order to extend the local solution to be a global one, we need a series of a priori estimates. The first one is we need the uniform boundedness of the moisture and the temperature. And this was proved by the temperature argument. For the QV, it is quite simple. We just test the QV equation with this QV minus QV star positive part. This QV star is determined by the initial date and the boundary variables. boundary functions. For the cloud water part and the rainwater part is slightly difficult than the QV. And for this one, we need test the QG equation with QG minus KG. KG is determined by the initial date and the boundary functions. And take the positive part and with index A. And then do the uniform the estimate on QG minus KG, the LM of this one, and then show that this one is independent of A. Therefore, we can take the limit m goes to infinity to get the upper bound of QG. For the temperature, this is the equation for temperature. Because of this one, we cannot do it in the same way as QV or QCQR. Because if you do in that way, you will need some a priori estimate of this ohmic. But at this step, we don't have any estimate on this ohmic yet. So instead we do change of variable. We define this potential temperature, and it turns out that this current term does not appear in the state equation, and therefore we can do the same way as QG, QR to obtain upper bound of state, and therefore for T. So then, based on that uniform bound, we can easily obtain the L2, H1 of V and T, because we have the dissipation on the velocity and the temperature. Then we need the H1. For H1, it's quite difficult because the system itself has the anisotropic structure. This can be easily seen in these two simple calculations. If you do the pressure derivative of this vertical convection term, then for this one, it's only the one derivatives involved. However, if you do the horizontal derivative, then for this one, we will have the two derivatives. So obviously, to deal with one derivative is easier than the two derivatives. And actually, the more severe thing is that the horizontal derivative depends crucially on the vertical derivative. So we always do the vertical derivative first, and then do the horizontal derivative. So for the V, we first do the L infinity H1 of V in the vertical direction. Before that, we need to do the L6 of V. L6 of V. And L6 of V can be obtained by decomposing V into the barotropic part and the baroclinic part. For barotropic part, it satisfies a 2D incompressible system. For the 3D part, the pressure is not involved due to the hysteretic approximation. And therefore, we can use the Linskaya type inequality to list 3D integral and then get the L6 of V. Then based on this L6 of V, we frequently use this the Linskaya type inequality to this type 3D integral. We can get the L infinity H1 of V in the P direction. Once we get this one, then the following estimate is quite standard. We can get the H1 in P direction of QG, and then the horizontal H1 of V and QG, and finally the H1 in all directions of T. So then we have the a priori estimate up to any finite time T, and therefore we can extend the local solution to be a global one. Here we know that the Holder continuity in QG of SEV does not bring us any actual difficulty, because at this step we only need the L2 of SEV to get all these estimates. The uniqueness. So as we said before, because this SEV is only Holder in this QR, So if we go directly in the standard way to show to do the energy estimate to the different system, we will end up with this kind of inequality. On left, we have 2 U's, but on right, we only have 1 plus bit. This bit, if strict less than 1, is less than 2. So this one does not give you the uniqueness. So to show the uniqueness, we need more careful analysis. We need the structure of SEV as a QR equation. We found that we observed that this SEV is monotone in QR, and in this energy estimate, we test with QR1 minus QR2. So we have brute term here. For this brute term, it is non-negative, and therefore this one we can just forget it and end up with this kind of inequality. And this one is fine for us to show the uniqueness. This is for QR. This tells you that this SEV is fine for us to in the QR equation. However, it is not fine for the QV and the T equation, because in this case, what we encounter is this latter one. For this latter one, we can only deal it. We can only use the information that QR bit is holder in QR, and therefore, what we end up with this kind of inequality. For this one, we don't have the uniqueness. Okay. However, how to overcome this difficulty is the idea is quite simple. Because this blue SEV is fine in QR, right? So we can just add this blue one to this red one to cancel this red one, and the same to this one, right? That means if we introduce this new Q and H, then in the Q and H equation, the SEV does not appear. And all other source terms are Lipschitz in the unknowns, and therefore it's Lipschitz in Q and H. So then we take QR, capital Q and capital H, and V as the new unknowns, and then we do the standard V. We can find the uniqueness for these new unknowns, and then go back to QV and QR. We have the uniqueness of the original system. Okay. So this is for the uniqueness. Now the conclusion and future works. We established the global well-posedness of strong solution to the primitive equations coupled with the multi-phase moisture system with phase changes. However, we need some assumptions. We assume all the individual gas constants for the dry air and the water vapor are the same. This is R. And we assume all the heat capacities of the gas and all phases of moisture are the same. And we use the ideal gas law. And in the future work, we will refine all these assumptions, remove all these assumptions that we consider the defined moisture system. And we will also consider the case with only horizontal viscosity. This is physically reasonable because the original system is for the atmosphere. For the atmosphere, we usually consider it as the ideal gas. That means no viscosity should be put in the system. And the reason that we put the horizontal viscosity there is because we have the strong turbulent mixing in the large scale atmosphere dynamics. But in the vertical direction, we don't have. So we put the horizontal viscosity is reasonable, but put the vertical viscosity is not. And we will also consider the multi-scale system, because in the atmosphere there is a combined system of many scales. And we will also consider ocean-atmosphere coupled system. Here we can just consider the atmosphere system and some related problem. So my talk is here. Thank you. And have a best day, Matthias.
In the the long-time behavior available even for the original PE?
Yeah, long-time behavior.
Yeah.
Oh, we have not yet considered this problem because here we consider the large initial date.
So our estimates are dependent on the T? Time
Yes,
T?
yes. But it's finite up to any finite time. So what we mean global well-posedness here is that the solution can be extended up to any finite time. Yes. And
So,
for the, say, we don't consider coupled system to the moisture, we can have some lifetime behavior.
Oh, okay. Thank you.
More questions? Maybe one on horizontal viscosity.
Yeah.
Because you mentioned this one. Can you tell us a little bit about the difficulties which arise when looking at horizontal viscosity only?
Yeah, here, if we, for this simplified system, that means under all these assumptions, then it's not so difficult to go there. But if you really want to go to this defined moisture system, even for the full viscosity case, we still have some problem. Yeah. And by the way, here we put all the dissipation in the moisture system. But actually, at least for the simple case, the simplified case, we don't need the dissipation for the moisture system. At least for at the level of a priori estimate.
If there are no further questions, then I thank the speaker and all
Thank you.